frequency distributions. First, we need to talk about what the meaning of the word frequency. The frequency of a value is just the number of times that the value appears in the data set. So here's our first example. I ask 5 people how many siblings they have, and I get these 5 answers. We need to count how many times each value appeared. 2 people said 1, so that value has a frequency of 2 because it appeared 2 times. 2 people said that they have 2 siblings, so this value of 2 appeared 2 times, so that value has a frequency of 2. And only 1 person said 3, so 3 has a frequency of 1. So we have 5 total answers, and 2 answers plus 2 answers plus 1 answer equals the 5 total answers. Here's another example. I asked 5 people how many classes they're taking this semester, and I get these 5 answers. 1 person said 1, so that value has a frequency of 1. 1 person said 2, so that has a frequency of 1. 1 person said 3, and 2 people said 4. It's also possible to organize these frequencies into a table. The table that shows frequencies is called a frequency distribution table. It has 2 columns. The X column shows all of the different values that appeared, and the F column shows the frequency of each values. So let's look at this first data set that we looked at the beginning. The different values that appeared were 1, 2, and 3. Those are the 3 different answers that appeared in here. And here I have them written as digits, even though they were written as words over here. And this F column just shows that the value of 1 appeared 2 times, the value of 2 appeared 2 times, and the value of 3 appeared only 1 time. So these are the 3 different values that appeared, and this is the frequency of each value. This would be the table for our second data set showing the number of times that each of these 4 values appeared. Here's one important point. The X column, the values in the X column are written in order, like 1, 2, 3, because if they're out of order, it doesn't look organized and it's difficult to read. Also, let's look at these 3 right here. In the X column, every value between the lowest value that appeared and the highest value that appeared need to be included. So every number from the lowest number all the way up to the highest number need to be included. 1 is both, in this data set, 1 is below the lowest number because the lowest number that appeared was 2. So since 1 was below the lowest number, we actually don't need this row right here. We can cross it off. Over here on the right side, the highest value that appeared was 3. No one gave an answer higher than 3, which means that we don't need this row right here. We can cross it off because it's above the highest number. But over here, this value of 2 never appeared in the data. No one ever said 2, but we still need to include it in the X column because it's between the lowest number and the highest number. If we cross this row off, our X column would skip over a number. It would be 1, 3, 4, and we don't want it to skip over a number. So that's why we just put the value of 2 right here and just say that it has a frequency of 0, meaning it never appeared. So we would cross these off. If we had this table, we would cross it off. If we had this table, we would cross this off. But if we had this table, we would write it out this way. Also, if too many different values are possible, you can create a grouped frequency distribution table. Here's an example. If I'm asking people, how old are you, and I'm recording people's ages, there might be many different possible ages that I might end up recording, because a person can be anywhere in a wide range of ages, because a person can live anywhere up to 120 years. I think that's about the record that longest a person has lived. So if I'm recording the ages of random people, there's lots of different ages that I might end up recording. And I don't want to list every age from 0 up to 100 in my X column. My X column would be very long. So instead of doing that, I might want to create these groups in my X column and just record the number of people in the 20s, the number of people in the 30s, and so on. That way, my X column isn't quite as long. And this, when the X column has groups inside of it instead of individual values, it's called a grouped frequency distribution table. So what we're seeing right here is that in my data set, 2 of the people were in their 20s, 1 person was in the 40s, and 1 person was in the 50s. No people were in the 30s, so that's why that has a frequency of 0. In a grouped frequency distribution table, each group of numbers is called a class interval. So each of these 4 rows right here is a different class interval. That's the first one, that's the second one, that's the third one, that's the fourth one. So we have class intervals in the X column and frequencies in the F column. This one has 3 class intervals. This one has 4 class intervals again. And the number of values that are covered by each class interval is called the class width. So we'll talk about the formula for the class width. But first, before we talk about the formula, I wanted to talk a little bit about what the class width actually is. So let's look at this first class interval here. This class interval covers 10 different numbers because there are 10 numbers in between 20 and 29. There's 20, 21, 22, 23, 24. That's 5 numbers. Then there's 25, 26, 27, 28, 29. That's 5 other numbers. So there's 10 numbers in between 20 and 29. There's also 10 numbers in between 30 and 39. There's 10 numbers in here, and there's also 10 numbers in here. So each class interval covers 10 numbers. That's why you would say that this table has a class width of 10. And the formula for the class width involves subtracting the number at the high end of the class interval by the number at the lower end of the class interval, and then adding 1 to your answer. I'll talk about what lower and upper boundaries are. These 4 numbers are called the lower boundaries of the class intervals. These 4 numbers are called the upper boundaries of the class intervals. To get the class width, you just have to pick one class interval. It doesn't matter which one you choose, and you subtract the upper boundary by the lower boundary, and then add 1. So let's take the first class interval and use it to calculate the class width. So if I take the first class interval, I'm subtracting the upper boundary of 29 minus the lower boundary of 20. When you subtract those two numbers, 29 minus 20, it equals 9. And then 9 plus 1 equals 10. So the class width is 10. And for this table. What about in this example? Well, we can see already that there's 20 numbers in here, there's 20 numbers in here, and there's 20 numbers in here, so the class width will be 20. But if we want to use the formula, we would pick a class interval, maybe just the first one, and subtract the upper boundary by the lower boundary, and then add 1. 19 minus 0 is 19, and then 19 plus 1 is 20, and that's our class width. This one would have a class width of 50. It's also possible to take a frequency distribution table and change it into a type of bar graph called the histogram. The histogram shows the same information as a frequency distribution table, but it makes the shape of the data more obvious. So I'll explain what I mean. Let's look at this data set right here. I ordered the values from lowest to highest. So maybe we did a survey. We asked 7 people a certain question, and these were their 7 answers. You can see already that 2 people said 1, 2 people said 2, 2 people said 1, 3 people said 2, and 2 people said 3. That's why it goes 2, 3, 2. What we could do is put each of these x values on a number line, 1, 2, and 3, and then turn each frequency into a bar. So we could put the value of 1 down on a number line, and then put a bar above that value to show the frequency of 1, and then put a bar above 2 to show the frequency of 2, and then put a bar above 3 to show the frequency of 3. Let's do that right now. So this histogram is showing the same information that the table did. Here's our first value of 1, and the bar goes up to the second tick mark, which is just saying that this value of 1 has a frequency of 2. And that just means that this value of 1 appeared 2 times in the data. Right here we see that the value of 2 goes up, its bar goes up to the third tick mark, which means that this value has a frequency of 3. It appeared 3 times. And this value of 3 had a frequency of 2 because it appeared 2 times. So what this shows is that we have a peak in the middle because that value appeared the largest number of times, and we have these lower bars because the values didn't appear as often. So when you look at a histogram, what you'll see is the histogram will peak at the values that appeared the largest number of times, and then it'll drop down when you get to values that appeared less often. And if you draw a curve around the histogram, you can see that the histogram follows a certain type of shape. Here's another example. This is another type. This is a common type of shape that we'll be looking at. The lowest value appeared the largest number of times, and then the higher values started appearing less and less often. We have 3 1s, 2 2s, and only 1 3 and 1 4. So if we made this into a histogram, it would peak at the left end because 1 appears 4 times. That goes up to 4. 2 only appeared 2 times. That goes up to 2. And these 2 values only appeared once. So when you have this type of a shape, it means that the lower values are appearing more often and the higher values are appearing less often. And it has this type of a shape where the curve that outlines the bars, it peaks at the left and then trails off gradually. This would be the opposite type of shape where higher values are appearing the most often because we have 3 40s but only 2 30s and only 2 20s. So here, the higher numbers are appearing more often than the lower numbers, which means the histogram will peak at the right end. There's 3 40s, but only 2 30s and only 2 20s. So it peaks at the right end and then trails off to the right. It peaks at the right end and trails off to the left. So now we'll talk a little bit more about some different types of shapes that can appear in a histogram. If it peaks in the middle and has a bell shape, and then gradually trails off in both directions, it's called a normal distribution, and in everyday life we often call this a bell-shaped curve. So here's what it looks like. It means that most people have values in the middle, and there's fewer people with lower values down here, and fewer people with higher values up here. A lot of types of data in real life follow this type of shape. For example, IQ scores are believed to follow this type of shape. Heights often follow this type of shape, and also scores on personality traits. In psychology, when you look at scores on personality tests, you usually see that there's fewer people with an extreme low amount of the trait, or an extreme high amount of the trait. Most people have medium amounts of the trait. The skewness of a data set refers to the extent to which the data peaks to the left of a normal distribution or over to the right of a normal distribution. So let's look at some examples. There's 2 types of skewness. If it peaks to the left of where a normal distribution would peak, and then gradually trails off to the right, it's called a positive skewness, or people sometimes instead call it skewed to the right, because it trails off gradually toward the right end, like this. So if it peaks at the left end, it's actually skewed to the right, because it's gradually trailing off toward the right. So a lot of people get these switched around. So you have to be careful to remember that this is skewed to the right, and this is skewed to the left. The reason why I put these arrows here is to make it stand out that this is actually skewed to the right, and that's actually skewed to the left. Because this arrow is pointing to the right, that's pointing to the left. If it peaks at the right end of if it peaks to the right of a normal curve, and then trails off gradually to the left end like this, it's a negative skewness, or you might just say it's skewed to the left. If a test is difficult, the scores of students in the class will be positively skewed, because there'll be a lot of D's and F's in the class, fewer C's, and even fewer B's and A's. If a test is really easy, the scores in the class will be negatively skewed, because you'll have lots of A's and B's, fewer C's, and even fewer D's and F's. Now since we've already covered the skewness of a data set, now we'll talk about the one new term called the kurtosis of a data set. This term refers to whether the data is flatter than the normal distribution, or has a taller and sharper peak than the normal distribution. Let's look at the 2 types of kurtosis. If the data has a shorter and flatter peak than a normal distribution, meaning it's flattened out more like a pancake, it's a negative kurtosis. If it has a taller and narrower peak than a normal distribution, it's called a positive kurtosis. So the skewness of a data set refers to whether it peaks too far to the left to be normal or too far to the right to be normal. The kurtosis of a data set refers to whether it peaks too low to be normal or too high to be normal. So skewness is when it shifted to the right or to the left. Kurtosis has to do with whether it shifted up or down. So we can see that a normal distribution is halfway between a negative skewness and a positive skewness. So you would actually say that a normal distribution has no skewness. And a normal distribution is also halfway between a negative kurtosis and a positive kurtosis. So a normal distribution actually has no kurtosis at all. So you could say that a normal distribution is a data set that has both no skewness and no kurtosis. And there's actually values that can be calculated to measure the skewness and kurtosis of a data set. If the skewness value comes out to 0, it means that the data has no skewness. It peaks right in the middle. If the further the skewness value comes out this way, the more dramatic of a negative skewness you have, and the further the value comes out this way, the more of a dramatic positive skewness you have. So if the skewness value comes out to a negative number, it means that your data is negatively skewed. If it comes out to a positive number, it means that your data is positively skewed. And the further the value is out here, the more dramatic of a negative skewness you have. And the further it comes out here, the more dramatic of a positive skewness you have. And if the value comes out somewhere between -1 and +1, you would say that the data has roughly no skewness, because it's fairly close to 0. Out here it would have a considerable negative skewness. Out here it has a considerable positive skewness. The kurtosis value works the same way. If the kurtosis value comes out to 0, your data has no kurtosis, meaning it doesn't peak too high or too low. It's right in the middle. If the kurtosis value comes out to a negative number, your data has a negative kurtosis. It's flatter than the normal curve. If it comes out to a positive number, your data has a positive kurtosis, meaning it's sharper than the normal curve. But if it comes out between -1 and +1, it's roughly no kurtosis, meaning it's peaking somewhere in the middle, not really high or really low. So the kurtosis value works the same way as the skewness value. So I said a perfectly normal distribution would have a skewness and kurtosis of 0. But if both values come out between -1 and +1, then the data has both roughly no skewness and roughly no kurtosis, which means it's roughly normal, or roughly bell-shaped. Let's look at some examples here. This data right here, this column of data, is negatively skewed or skewed to the left. This data set is positively skewed or skewed to the right. This actually isn't an actual data set. It's just a picture of a normal distribution that I copied and pasted. I just wanted it to be in the middle to use it as a reference so that we can compare it to these other two data sets. So this would have a skewness and kurtosis of 0. This has a negative skewness, so the skewness value is negative. It's about -1, and so that's about at the point where it's considered a considerable negative skewness. The kurtosis is a little bit below 0. So meaning most of it is fairly flattened out. There is this peak right here, but if the peak was up if this peak went up higher and it was more of a sudden peak, if it went up, like if it was taller and went up really abruptly, that would be more of a positive kurtosis. So sometimes it's hard to judge, really. I think kurtosis is a little bit harder to judge just by looking at it than skewness is. Skewness kind of often stands out more clearly. This has a positive skewness because it's positively skewed. And notice how this is just the mirror image of this. So even though this is a negative skewness and this is a positive skewness, the skewness is equally dramatic here and here. They both have the same amount of skewness, just in different directions, which is why the skewness value just comes out to opposite numbers. This is pretty flattened out, so the kurtosis value should be negative. Yeah, it's a fairly dramatic negative kurtosis. It's past -1, but it has roughly no skewness. The skewness is pretty close to 0, which makes sense because it's peaking in the middle. This should be a positive kurtosis. Yeah, it's slightly positive, 0.26. And it also doesn't have much skewness because it's peaking pretty close to the middle. So one last point I wanted to go over is that the position of the mean, median, and mode depends on the shape of the data. If the data is positively skewed, the mean is above the median. The mean is on the right side. The mean is on the right side of the median. If the data is negatively skewed, the mean is below the median. In other words, the mean is on the left side of the median. So when the data is skewed, then the mean is pulled out toward the tail. Here it's pulled out this way. Here it's pulled out this way. And the amount that the mean is pulled away from the median depends on how much of a skewness you have. If it's a more dramatic skewness, it'll be pulled out further. If it's only slightly skewed, the mean and median will be pretty close. And remember that the mode is the peak of the data. It's the peak of the curve because that's the value that's appearing the largest number of times. So what actually happens is if the data is normal, has a normal curve, the mean and median are both equal, and the mode is actually at the same place because that's the peak right here. So when you have a normal distribution, the mean, median, and mode of the data are all equal. This is just one last example showing how when you have this negative skewness going out this way, the mean, well here, the mean is a little bit to the left of the median, like I said it would be. This is a positive skewness, which means that the mean is a little bit above the median, like I said it would be earlier.